So just a moment. So, up and down with this. Okay. Okay, so the topic of my talk will be on a joint work with Lorenzo Cristoforo, who is our PhD student in our department, and also with Gaida, who is research professor of University of Warsaw. I will speak about this so-called what we call gamma gray Brownian motion. I will introduce it, but before I will give some notation and definitions which are important for understanding the construction of this process. So I recall very shortly one of the representation of the fractional Brownian motion. Then I will recall the property of complete monotonicity of functions, because this is the key property that we use in the following. And I recall the so-called white and gray noises. And based on this, also the concept of generalized processes. And then the incomplete gamma function, which is also very important for these constructions in our case, in our particular case. And then I also recall some preliminary results on this upper incomplete gamma function, and then we will move to the main results and some further hints to some further research directions. So first of all, very shortly, one of the representation of the fractional Brownian motion is given by the Mandelbrot-Van Ness integral. So if we consider W the two-sided Wiener process and this kernel K8, H is always capital. There is a mistake in the first formula. H is the well-known Hartz parameter, so it is between 0 and 1. Then the well-known fractional Brownian motion can be defined by means of this stochastic integral with respect to the Wiener process up to the constant CH, which is written here. In particular, it will be important for us the last representation, the last definition, which is equivalent to the first one for the fractional Brownian motion, which uses this operator MH, M capital H, which we can define as basically as a simple Riemann-Liouville integral, but the order K can be also negative. So in the case it is negative, it is a Riemann-Liouville fractional derivative between x and plus infinity. So the right, so this is why we have the minus in the bottom. Then the fractional Brownian motion can be represented as this last formula, last stochastic integral with respect, which is an integral with respect to the Wiener process, but the function inside is the operator MH applied to the indicator function of 0t. And this is very important for us because we will refer again later to this operator. But before, I just recall the very well-known definition of completely monotone functions. So a function f on the positive real semi-axis is completely monotone if it is C infinity and signs are alternating between for the order passing from odd to even orders. Then there exists, it is well known for the mean-loss theorem that there exists a unique measure mu such that the following expression to which also Bruno was referring earlier as basically as Laplace transform plus a drift, but in our case, the A and B constant will be always equal to 0. So basically F can be expressed as the Laplace transform of this measure mu. And then there exists a unique characteristic functional on an Hilbert space H such that this phi of xi is equal to the completely monotone function f applied to the squared norm of xi. There are a lot of examples of completely monotone function. Even the simple negative exponential is completely monotone, or the negative exponential with power alpha for alpha in 0, 1, and also, which is important later, the Mittag-Leffler function is for beta in 0, 1. In any case, we will use the Mittag-Leffler negative argument, and it is completely monotone. Of course, I recall that Mittag-Leffler function for beta equal to 1 reduces to the exponential function. So, bearing this in mind, now we move to more complicated spaces. So we will consider the space of Schwarz test function, so rapidly decreasing function with all the derivatives, so smooth function with all derivatives rapidly decreasing to 0. And its dual S prime. Of course, S is a subset of a subspace of L2, which is a subspace of S prime. And we define so the capital F as a completely monotone function on S. Then there is an analogous result analog to the one that I mentioned before. It is in this space called the Bochner-Millos theorem. So this states that there exists a unique functional phi, again, such that this is true. And again, the unique measure, in this case, on the space S prime, on the dual S prime, is uniquely defined. And this is very important because it states the one-to-one correspondence between characteristic functionals and measure in this space S prime. Then, of course, if we choose f equal to the negative exponential, then we have the well-known Gaussian measure or white noise measure. And then we call this space as white noise space. If instead of this, instead of the negative exponential, we choose the Mittag-Leffler function with parameter beta in 0, 1, then we have this functional phi expressed by by means of the Mittag-Leffler function, and the measure is called gray noise measure. So the space is called gray noise space. This is basically was introduced by Schneider in the 1990, more or less. Later I will give you the references. Then, based on this, there are some different approaches, but equivalent approaches to that permits us to construct a so-called generalized process on this space S prime with the measure mu that can be chosen in different ways. Then by the dual pairing operation, and then if again the measure is the white noise measure that now I denote by M1, because it is a particular case of mu beta for beta equal to 1. And if we choose the argument phi as the indicator function, we are back to the standard Brownian motion. Otherwise, for when the space S prime is endowed by the measure mu beta, then we get the gray Brownian motion. The further step has been taken by these authors there in two different but equivalent approaches, by Grothaus and his co-authors on one side, and earlier by Mura, Pagnini, and Mainardi. they constructed the so-called generalized Gray-Brownian motion by means of this operator, which is essentially the one that I have introduced in the first slide. Here, just we choose h equal to alpha over 2, but the operator is essentially the same. I forgot to write there that it is a Riemann-Liouville integral for alpha in 0, 2, but excluding 1, while for alpha equal to 1, of course, it gives the function f, identical to the function f. So this generalized Gray-Brownian motion is defined by means of the dual operation when the space is S prime with the norm mu beta for a general beta in 0, 1, and it is applied to not directly to the indicator function, but to the operator m alpha over 2, the operator function in 0, t. So this property, this process, okay, here again I wrote the characteristic function of this process, and here you can see that again for alpha equal to beta you get the Gray-Brownian of the Schneider Gray-Brownian motion. For beta equal to 1, the Mittag-Leffler function reduces to the exponential, and then you have the fractional Brownian motion, because again you are back to the first slide definition of the fractional Brownian motion. And for alpha equal to beta equal to 1, simply the standard Brownian motion. So this generalized Gray-Brownian motion is a model of anomalous diffusion. The covariance is just the rescaled covariance of fractional Brownian motion with this constant, depends of course on beta. It's a cell-similar process with stationary increments, and it was proved by Mainardi and Mura that its marginal density is the fundamental solution of the stretched time fractional master equation that I will show you later. So this is just a joke. The idea was to replace the Mittag-Leffler function, which was called by Francesco Mainardi the queen function of fractional calculus, because indeed it is a very, very basic and important function in fractional calculus. And as we have seen, it is the key function for the construction of the generalized Gray-Brownian motion. Our idea was to replace this by the incomplete gamma function, which was defined by another Italian mathematician in the 19th century, a Cinderella of special function, because of course it is another basic function. And then based on this, we will construct the so-called, what we call the gamma generalized Brownian motion, gamma Gray-Brownian motion. So just to recall the definition of in particular, we will refer to the upper incomplete gamma function. So it's the integral from x to plus infinity. There is a preliminary result, which is not very important in the following, but just to recall it. The upper incomplete gamma function is, we have proved that it is coincides with the solution of this fractional relaxation equation, where the derivative, the operator is given above. We have the kernel, which is in terms of incomplete gamma itself. Of course, for I forgot to that obviously for rho equal to 1, the incomplete gamma function reduces to the exponential function. So in this case, for rho equal to 1, we have the ordinary relaxation equation, and the solution is, of course, the negative exponential. But what is more important for us now is that the upper incomplete gamma function is completely monotone, and we can obtain the measure, this measure nu rho, which is uniquely identified by means of this relationship and the mean-loss theorem. And the measure can be written in different ways. One of these ways is by means of the Meillet function, which is a particular case of H function, hypergeometric functions. So what we did with these results, we wanted to first to use the moments of this measure in order to apply the Gram-Schmidt orthogonalization to the space L2, then define the infinite dimensional measure on S prime, the dual of the Schwarz test function space, and construct the Brownian, the gray noise space as for the white noise space and the gray noise space, and then define finally the generalized process as before for this particular measure. But the first problem was that the moments of Niro are infinite, and then we had to introduce a tempering parameter, theta. Of course, for theta equal to 0, we are back to the previous measure, but we need to take theta greater than 0 so that the moments are not infinite. And in fact, we evaluated the moments of this measure, which are expressed by means of the Prabhakar function for even order moment, while as for the fractional Brownian motion and the Brownian motion itself, the odd order moments are equal to 0. Then, as I said, we could use this result to construct the polynomials which are orthogonal in L2 with respect to the measure nu rho theta. And of course, this for rho equal to 1, this polynomials reduces to the Hermite polynomials. Then we could define, we can go a step forward and define the infinite dimensional gray noise measure on S prime, as was done for the gray noise, and by means of, again, of the Bochner mean-loss theorem. Then, as I said before, many times, for rho equal to 1, this space with this norm reduces to the white noise space. Why for rho different from 1, we call this space gamma gray noise space. And then we can define the generalized process by means of this dual operation when we take as an argument again the operator m with an order 1 minus alpha over 2 applied to the indicator function. So we have studied all the properties of this process, the n-time characteristic function, and this is an equivalent definition, but I want to skip it for shortness of time. And I can just give you some characterization of the process. This is a full characterization. It means that it is for any finite dimensional distribution, not only for the one-dimensional distribution. So our process is proved to be equal in distribution to a fractional Brownian motion multiplied by an independent random variable, the square root of h and of y, and y theta lambda rho is a random variable with this density, which of course is connected to the measure that we have introduced before. Of course, for theta equal to 0, we have a simpler expression, but again, the moments are not finite. And we can evaluate the moments of this process and the autocovariance function. Of course, the moments for theta equal to 0 are, and also the covariance are infinite. And it is proved to be, again, but it is very easy to see that it is stationary, it has stationary increments with this characteristic function and order continuous. And it is self-similar as the fractional Brownian motion with parameter alpha over 2. So actually, our gamma gray Brownian motion is defines a class of H stationary, self-similar stationary increments processes with H equal to alpha over 2, which includes the fractional Brownian motion for ρ equal to 1 and the Brownian motion for ρ equal to 0 to alpha equal to 1. I can also give a time-changed representation for the only for the one-dimensional law of this process. This is similar to what happens for the gray Brownian motion. So we need to introduce before this process y of t, which is of course for t equal to 1. At time t equal to 1, it reduces to the random variable introduced before. And then this process is self-similar, but with scaling parameter equal to 1, as stationary non-independent increments and non-decreasing trajectories. So it can be used to time change the standard Brownian motion in this case. So if we consider a standard Brownian motion B, time changed by this process with the time parameter stretched, so to a power alpha, then of course we assume that B and Y T are independent each other. Then it can be proved that our gamma gray Brownian motion is equal in distribution in the sense of the one-dimensional distribution to this time changed Brownian motion. Based on this and with some analysis, we can we prove that the characteristic function of our process for theta equal to 0 satisfies an integral equation, which is written here. And inside the integral, we have this function E rho, which is so-called rho exponential function and is expressed itself by the Mittag-Leffler function. Then it is not very easy to see that for rho equal to 1, the two exponential, the standard exponential and the rho exponential simplify, and then we are this equation reduces to the equation satisfied by the characteristic function of fractional Brownian motion, as of course should be. But for rho less than 1, so different from 1, we can compare the previous equation with the equation satisfied by the Fourier transform of the master equation that I mentioned before, which is the equation, differential equation, integral differential equation satisfied by the density of the gray Brownian motion. And apparently the two equations are similar, so this the one in the bottom and the previous one, but if we look at this very more accurately, we see that here we don't have exponential, of course, and while here we have the two exponentials. So they are different. And also again in the special case theta equal to 0, so when the tempering parameter is equal to 0, we have also obtained the differential equations integral differential equations satisfied by the density of this gamma gray Brownian motion. And of course, if rho is equal to 1, we are led to the integral differential equation satisfied by the density of the fractional Brownian motion itself. So just, okay, the initial conditions are obvious. So just some hints to the further research directions. Of course, we have some other work to do in order to study some other features for this process. So local times, Feynman-Katz formula, as done for the usual gray Brownian motion. Also, we are trying to generalize the analysis that I have described so far to the case of a more general completely monotone function, of course, under some appropriate conditions. And also, we were thinking to generalize the above definitions by means of more general fractional operators, more general than these MH or M alpha over 2. Operator using the theory by Kochubey and the so-called general fractional calculus. So just some references. The first one is already published, but the big part of this talk is in a paper that is still in preparation. And there are here some references basically on the usual gray Brownian motion. So in particular, the approach that I have described is in the papers by Grothaus and Grothaus-Janert, and different but analogous approach is you can find in the papers by Mura, Mainardi, Mura, Pagnini, and then the paper by Schneider is the previous article where the gray noise is presented. So I think that's all. Thank you very much for your attention.
Thank you, Luisa. Any questions or maybe comments, please? Yep.
Yeah. Sorry. Yes. Hi, nice to meet everyone. So I have a question related to the generalization. So of course, there are many completely monotone functions, and there are then a lot of interesting possible new processes that can be discussed, etc. But is there a way of writing maybe a very general theory, or is it perhaps just the idea that is general and it's not possible to write a general theory?
We hope that there is the possibility to generalize the theory. Of course, there are some constraints, so we cannot choose any completely monotone functions. In particular, in order to define this probability space with obtain the measure, this measure must satisfy some constraints, which are satisfied by in the cases that I have presented. But of course, for other more general case, we have to check if these conditions are satisfied. But we hope to find other completely monotone functions that can be useful for this generalization. So we are trying to do this, but I cannot give a final answer to this question.
Okay, thank you for the question and for answer. And any other questions, comments from audience in Zoom? How we can hear it from them? I mean, yes, ask maybe some people who are
they have to ask it in the chat, or can they feel free to unmute themselves? There's
They
nothing in
can
the
now.
chat so far, but.
So now we have a half an hour break, coffee break.